Hello everyone, my name is Abebual Molla. Today I'm going to give a talk about my research entitled with combining form thick protein other layers in water ethanol mixtures by using glutaraldehyde for cross-linking. When we see the background of the study, we try to start our study depending on our reference paper that was published by Tan and his friends. So they try to find out the absorption of protein on silica surfaces. They study the interaction of protein on silica surfaces. So as you see from the figure, as the concentration increases or the ethanol fraction increases, the cross-linking behavior of and the change in morphology of the molecules of protein also changes. So here we try to use BSA. As we know, BSA is derived from cows and it's often used as a protein concentration standard in laboratory experiments. So depending on the first paper, we continued how we can cross-link proteins on surfaces. We studied that. Previous studies shows that different morphological changes due to ethanol and protein or base interaction. Tan and his colleagues studied the interaction with pure water, low ethanol fraction and high ethanol fraction. So the absorption capacity will vary depending on this concentrations. So they showed with 0%, 10 to 30%, and then 40 to 60%. So as we see from the figure, in 0% there is only low packing density, and it's increasing with 10 to 30%. It will have higher packing density, and then with higher concentration of ethanol fraction, there will be high packing density and structural reorganization of the protein molecules. So the tested ethanol fractions are from 0, 10, 20, 30, 40, 50, and 60. And we can see the native BSA in water ethanol mixtures and the conformational stability changes, and then after it's absorbed or morphology is changed, the protein absorption in experiments also showed from their work. So depending on the first paper, we try to solve the problem that they were facing. From the first paper, we already know that basic can be easily attached or absorbed on silica surfaces with different concentrations of ethanol, but finally after absorption, if it's washed with water, it will go back to its initial state. So we need to solve this problem, and then we try to find out a solution for this. So we need to cross-link the protein. So we solve this problem by using our own mechanism to cross-link the protein. So this is the overall protein cross-linking method. So we try to check with buffer protein, and then with buffer wash after like cross-linking. So as we see from the figure, even if the protein is cross-linked and then washed, it will not go back to its initial state. Therefore, the overall our work is like protein molecules will be crystallized and then will compact together. But if they washed, they will go back to their initial state. Therefore, we use glutaraldehyde for cross-linking. So even if we wash them after cross-linking, they will not go back to their initial state, as we see from the figure. So this shows the cross-linked protein crystals that will not go back to their initial state. So from Tan and his colleagues' paper, their finding demonstrated like how ethanol-induced conformational changes in the BSA protein structure can modulate the extent of protein absorption onto silica surfaces, and more broadly, they highlight how solution phase conformational stability is an important factor in dictating how proteins absorb and denature at the solid liquid interface of the, the material or the surface that we are using. But in our findings, we demonstrated how ethanol fractions affect the deposition of BSA protein on silica surfaces, and then glutaraldehyde cross-linking to maintain ethanol-induced conformational changes to have a better saturation and create more rigid layers packing, which is much beneficial for drug delivery and coating applications.